In this video, I'm going to cover section 3.2 and 3.3. Okay, so 3.2 cumulative distribution functions. So let's just jump into the example 3.5. This is the channel. Okay, so the question is to find the probability that x is less than or equals 3. So the cumulative distribution is, you see, that probability that x is less than or equals 3. That means x can be any discrete random, any values of discrete random variable less than or equals 3, right? So now in this example, so they're gonna use the table in example 3.3. So you might be interested in probability that 3 or fewer bits are in error. So that means there's no, starting from no 0 bits in error to up to the 3 bits in error, right? So then P of x, probability x is less than or equal to 3 equals what? P of x equals 0 plus P of 1, P of 2, P of 3. Okay. So now then so here the the function, probability mass function, and then the left the represent the not just the probability for one value of random variable, but the certain values, the certain group of values is called the cumulative distribution functions. Okay, so now then, so the cumulative distribution functions, uh, denote the probability of such, like this: probability that x is less than or equals specific values, okay, or x is greater than or equals specific values, but usually x is less than or equals certain specific values. Okay, so now then, so these values from the example, the data in the example 3.3. Okay, so now then, let's see the definition of the cumulative distribution function. um, Let me just say CDF. Okay, that stands for cumulative distribution function. So this definition of CDF is this: f of x, they use a capital F. Okay, lowercase f represent a probability mass function in section 3. Okay, chapter 3. And then capital letter F represent is denoted by what? CDF. Okay, so that is equal to P of x is less than or equals x, which is the sum of the all of the probability mass functions of xi, and then the xi is what? Is less than or equals lowercase x. Okay, so now then, yeah, and then in general, for any discrete random variable with the positive values x1 through the, you know, maybe there are infinite number of the values, maybe, but all the events x equals x1, x equals x2 are mutually exclusive. Okay, so the, let's see, and then look at this one. The properties of CDF. Okay, for discrete random variable x, the CDF satisfy the following property. So CDF is equal to, yeah, we haven't seen this one in the definition. Okay, so we'll see that. And then CDF must be between 0 and 1. Okay, and then for x is less than or equals y, so lowercase x, lowercase y, okay, lowercase y, letter y, just those these are represent what? Specific values of uh, the random variable. Okay, but x is less than or equals y, then CDF must be less than or equals the CDF y. Okay, so it means that what? CDF must be increasing functions. Okay, that one represents what? CDF must be increasing functions. So now then, now let's see. Look at the example. Okay, so the, let me see. So f of let's see example this one from the example 3.5. Okay, so where is example 3.5? Give me a second. Yeah. See. Oh yeah, here. Okay, example 3.5 here. So P of, see, x equals 0 is this 0.6561, and then you see that these numbers here. Then we can say that f of 0 must be 0, and the f of 1 means that what? So give me a second. So here the CTF, the textbook can be they figure out like this by using definition of CTF. So if x is between greater than or equals 0 and less than 1, then x must be 1, right? X must be 0, right? So because x is less than, x cannot be 1. So f of 0 is p of x equals 0. Okay, that's simple, right? So in this case, that CTF is nothing but just PMF. PMF means that probability mass function. And then x is greater than or equals 1, less than 2, then that means what? X can be just 1. Keep in mind this, that x is what? Should be the integer, okay? I mean the natural number, because this is discrete random variable. So x is greater than or equals 1, less than 2. Then what number can x be? 1, right? So f of 1 is what? Probably p of x is less than or equals 1, which is p of x equals 0 plus p of x equals 1. Okay. So likewise, we can figure out f of 0 through f1 to 3 and f of 4, right? To f of 4. So this is equal to probability that x is less than or equals 4, right? Okay. So now then, the through the what? Then what if we just, I mean, last one must be 1. I mean, if the what? X is the greater than or equals 4. Okay. So now then, the here, let me plot the graph of this one. Okay. So the value of each one is given in the textbook. Okay. Look at this. So when x is 1, I mean, here the x-axis. Okay. So this is the CTF, reference CTF. Okay. Is at 0. Okay. 1, 2, and 3, and 4. Okay. So when x is 0, then I mean, when x is between 0 and 1, okay, then f of 1 is in the textbook says is 0.6561. So point is here is 0.6561. Okay, 0 is included, and then 1 is not included. Okay, and then greater than or equals 1 and less than 2, the value gonna be what? 0.9477. Okay, let's say here's a point. Let's say here's a 0.9477. Now you see it here. Okay. Then now the next one, f of 3, f of 2 gonna be, this is 2. That's gonna be what? 0.9963. Okay. 0.99, maybe right there. 0.9963. Okay. So maybe right here and like this. Okay. So here the f of 0, f of 1, f of 2, f of 3, f of 4, these are just doesn't represent the what CTF at just one value, 0, 1, 2. No, for any x between a greater than or equals 1 through 2, each CDF gonna be equal to f of 1. Okay. Okay. And then for any value, for any x between, I mean, greater than or equals 2 and 3, their what? I mean, is CDF gonna be equal to f of 2? Okay, that's what we're gonna get. This kind of step function. This is called step function, right? You haven't seen this one in the calculus one. So now and then f of 3 gonna be maybe like this. Okay, right here. And finally reached 1. Okay, here's a 1. There's a 1. Okay, so here's a 1. Okay, so now then as you can see that what the probability that, for example, give me a second. Okay. Oops. Now we can use the CDF to figure out PMF. Okay. So for example, so think about this. I want to figure out probability that, I mean, f of 3. Okay, f of 3 means the probability that x equals 3, right? Okay, so how can you use the CDF to figure out PMF? So let's figure out this one, f of 3. F of 3 is what? Probability that x is what? Less than or equals 3, right? Okay, that is equal to probability that x equals 0 plus through the probability that x equals 2 plus probability that x equals 3, right? So now you see that here, this part, x equals 0 through the x equals 2, that's nothing but what? F of 2, right? Okay, so now what? Then the see here, f of 3 is equal to f of 2 plus p of x equals 3. But this is nothing but what? PMF, f of 3, right? So f of 3 is equal to what? F of the CDF f of 3 minus CDF f of 2. You see? Okay. So now probability that x equals x 3. I'm sorry. So f of 3 is equal to f of 3 minus f of 2, right? Okay. In general, okay, generalize this one. Look at this. Probability that x equals xi. Keep in mind, this is equal to what? F of xi, right? So that is equal to f of xi minus here minus uh, the now let me see, xi minus 1, or yeah, we can do this f of xi minus 1. Okay, you can say that in this example. Okay, but depending on problems, maybe xi minus 0.5, or yeah, so point 0.1, point 0.2, point 0.3, point 0.4, point, 0.5. These also can be considered as a discrete value, right? So generally, this one there is a better expression than this one, because this is only worked in that example. But I want to fully generalize that concept. Okay, it's going to be limit of f of x and then x up jump to xi. Okay, what that means? That means nothing but the this x never equal can be that because of limit x never equal to xi, but x just approach the one less level, or one less the discrete value than xi. Okay, so that's the meaning of this. Okay, I know you haven't seen this kind of notation in the calculus, but you don't have to be familiar with this symbol. Okay, but just understand what that means. Means that just in this example, f of xi minus 1. Okay, so now see back to the textbook. So right here. All right, so example C, example 3.6. Now example 3.6 is similar to the example what we have seen right there. So now you say determine the probability mass function of x from the following CDF. Okay, so the f of x is given here. Okay, so the graph is like this. Keep in mind is you should know how to plot the graph of CDF by from the definition of CDF. Okay, all right. So the key in mind is, or you can just figure out the definition of CDF and the definition of the PMF by looking at the graph of CDF. Okay, these kind of problems will be on the homework assignment. Okay, so you see that x is less than negative 2, f of x defined by 0. So you see that that's what we got, that one. See. Okay, and then between -2 close interval, -2 to open 0, the f of x is defined by 0.2. Okay, so what that means here, that means the f of -2, you see, f of -2 must be 0.2. Okay, the f of negative, f of x must be 0 on any x value from -infinity to the through the what the negative, close to -2. Okay, close to -2. Okay, see, close to -2, right? And then when x equals -2, then PMF has value which is -0.2. 0.2. That's why the CDF jumped to the 0.2. Okay, and then what f of the, and then f of, for example, f of -1 is still 0, and then f of the, for example, -0.5 still 0. Okay, all the, I mean, PMF at any x value between greater than -2 then less than 0, 0. But why we got the point, I mean, that 0.2? Because this is CDF. Okay, even though the PMF at x equals any value between open -2 to open 0 is to 0, is 0. Sin the Because the CDF, I mean, f of -2 equals 0.2. That's why CDF is still 0.2. Okay, it's cumulative. Keep in mind this. And the f of 0 is just not 0.7, 0.5. That's why 0.5 plus 0.2 equals 0.7. That's why we got the 0.7 in CDF. Okay, that doesn't mean that f of 0 is 0.7. No, f of 0 must be 0.5. Why? Because see that 0.7 CDF, the value of CDF, I mean, CDF at x equals 0 is 0.7, means that what? It means that 0.2 plus something equals 0.7. What's something? That must be 0.5 at x equals 0. So that's why we got the 0.7 right there. So it means that PMF at x equals 0 is 0.5. We see here right there. Okay. See? So now through this, we can figure out all the PMF. Okay, you see that? So, and then, or you may just use that formula. Okay, so I told you what's the limit of this. That's nothing but just what? In this case, for example, f of 2, when you calculate f of 2, 1.0, that's the what? CDF at x equals what? 2. CDF at x equals 2 is what? 1 minus, and then CDF at x equals what? 1 less discrete value than 2. Okay, so, or just the before less step right there, which is 0.7. Okay, that's, I think, mm, yeah, I think that in that way you're gonna get the better understand. Okay, so 1 minus 0.7, which is 0.3. Okay, so now we move to the 3.3 and mean and variance of discrete random variable. Okay, so now we're gonna see a little bit more mathematics aspect of mathematics. Okay, so let's see. Okay, look at the first paragraph. The two numbers are often used to summarize the probability distribution for random variable x. Okay, so the mean is a measure of the center or middle of the probability distributions, and the variance is a measure of the dispersion or variability in the distribution. So simply saying that mean is one of the tool to measure the center of the mm, sample space, and the variance is one of the tool to measure the how spread out the data. Okay, the standard deviation, we'll see that standard deviation is the square root of the variance. Okay, given this. So mean or this is yeah. So see, these two measures do not uniquely identify a probability distributions. No, I think there are a whole bunch of different way to measure tool to measure the center of the data, and then the tool to measure the you know dispersions and the variability. Okay, so it's not unique, and then that is a two different distribution can have the same mean and variance. Oh yeah, sorry, that's me. I made a I be understood. So that the not unique means that, even though two sample space has the same mean and variance. Okay, so their data values may be different. Okay, so now still these measures are simple and the useful summarize of the probability distribution of x. So actually mean and variance these are just called the discrete. We're gonna use them to in the discrete statistic. I'm gonna talk about this one later, but there are two types of the statistic: discrete statistic and then inferential statistic. So discrete statistic is this is to summarize the data and then visualize the data so that the customers or people can easily understand the data. Okay, how many people just how many data is just, the um, the the gathered on certain positions, or how this spread out the data, and then which in an area has a large probability, something like this. So the that's called the discrete statistic, and the inference statistic is to use the sample data to approximate the characteristic of population. So population, when you look at watch it the when you study the lab, you may heard about the population. Population is just whole group. For example, so I want to just figure out the mean of the math score in not just this school, but entire, the college, the entire college in US. The entire college in US gonna be population, but it's expensive, or it's hard to figure out the you know the mean of the math score in the entire US college, right? So we just collect um, the select the some of them randomly. That's gonna be sample space. It's called a subset of the whole the U.S. college, which is population. Okay, so now then we're gonna calculate the mean of the randomly selected U.S. colleges, and then we use this one as approximation of the mean of the population. Okay, that is one of the example of inference statistic. Okay, so inference statistic is to approximate mean or standard deviation, variance, of the proportions. These are called the actually parameter, which the parameter means the characteristic of the population. Okay, so approximate the parameters of, okay, or something else, but we're going to talk about this later. Anyway, we're going to start from the mean, where mean is called the expected value. Keep in mind, is the mean expected value are not equal to average. Okay, we don't normally, statistician don't say use the word average. Okay, so the mean or expected value of the discrete random variable x denoted by as mu. Yeah, mu or e of x. Okay, so mu of e of x is defined by sigma of x times f of x, and the variance of x is denoted by sigma square. You see the lowercase Greek letter sigma right there, square, or v of x. Okay, so sigma square is v of x defined by e of x minus mu square. Okay, you see that x minus mu is what? Difference between the what? Difference between the mean and the random variable, then find the mean and square, right? Okay, I mean, in the take a square and then find the mean of that value. So sigma x minus mu squared times f of x. Okay, that is equal to this. Yeah, so the why this is equal to this? I proved this one in the lecture note. Okay, let's see. So in the lecture note right there. So why is sigma squared and the variance is equal to this? Because the starting from definition of v of x is sigma x minus mu squared f of x, and then we're gonna just the FOIL, okay, x minus mu squared. Then we're gonna get this x, and then so sigma satisfies linearity. Okay, so then we can the breakup that sigma into sigma of x squared times f of x minus 2 times the mu times x times f of key minus mu is a constant in the view of sigma, okay? Because x is a moving index, so mu is constant, so we can bring it out. Okay, that's what we got. This negative 2 times mu times x times f of x. By the way, sigma x times f of x is what? Mu. That's the definition of mean, right? Okay, and then plus mu squared times sigma f of x. By the way, what's f of x? PMF. So sum of all of the PMF must be equal to 1. That's one of the what? The condition of the PMF probability mass function, right? So sigma f of x is 1. Negative 2 times mu times mu, which is a negative 2 mu square, plus mu square is a negative mu square. So that's what we got this. Simple, right? Now let's see example 3.8. These are generic, excuse me. In this example, yeah, the problem asks you to find out the mean and the variance using the formula. So here, definition of mean and then the definition of variance. But yeah, you can just but um, let me introduce how to find out mean and variance in the standard deviation using the TI series calculator. So here in the when you first one, you have to enter the data first. Okay, so we have to go to we press stack. So this is a TI-84 plus. That's the yeah, see, this is TI-84 plus, but TI-84 and TI-83 so similar, really similar to the how to find out the how to do this with the TI-84 plus. Okay, if you have TI-89, then you can just search the YouTube or the internet. Um, then you can find out how to the instruction how to do that. Okay, so now then, so first one, you go to the stack here. Okay, then there are 3 tabs right here, and then edit and calculate and test. Okay, so we under the edit, we go to the edit. Okay, so just okay, then here you have a whole bunch of columns. Okay, so each column we can enter data. Okay, so actually I already entered the data in column L14. For your calculator, you may have only L1 to L6, but you can the uh, create more columns. Okay, so for example, I have a L. So we just go to the column name L16 and then move to the right. Then the you see that here I had 17 columns here, and then from the column name L17 moved to the right, that was created. And they see that here the calculator just asked me to enter the new column name. Okay, so press alpha and then L. Give me a second. L. Okay, and then this should be 18. Okay, then I just made a new column. Okay, anyway, so I enter the data here. What does it mean data? So first one, L14, you need to enter the list of values of random variable. Okay, 0 through the 4. In this example, 0, 1, 2, 3, 4. These are the possible values of random variable. And the other columns, you have to enter the probability. Okay, so corresponding to each values of the random variable. Okay, so I enter the probability here, and then now press stack again. We go to the calculate tab, and then we select the one variable stack. You see the one variable stack right here, variable stack, and then list here. They're gonna and ask the list and frequency list, and then list we enter the column name of the values of random variable. Because I entered the values of random variable in the column name L14, so I put the L14. And then frequency list, you enter the column name of the what? The list of the probability. For me, I just enter the probability F15, and then you calculate. Now, then you see that sigma x bar. That's the actually x bar is the symbol of the sample mean. Okay, but the in textbook they use a mu. Okay, in probability they use a mu, but keep in mind x bar means the sample mean. But in this case, uh, in the problems, x bar is nothing but mu, so 0.4, that's the mean, okay? And this is sigma x, that's the Sx, you see the xx, that's a sample standard deviation, and sigma x is population standard deviation. Okay, so sigma x 0.6, that's a population of that example. Okay, because in their example, there is no there is no what the what sample space, and I mean sample space and then the population are distinguished. So okay, so we don't have to really care about the notations. Okay, so the x bar, that means mean. Okay, and then the sigma x 0.6, that's the standard deviation of the data. Okay, so now what's the variance then? The square of 0.6, which is 0.36, that's going to be variance. Okay, this is how to find out the mean and variance using calculator. Now the look at this. And the next one is the a little bit the second version of the expected value. Okay, so the expected value of function of discrete random variable. So first we learned the expected value of just the random variable x. Now we want to we're studying the expected value of a function, but that function is the that function represent our PMF. Okay, so it's the E of h of x. So expected value of the h of x. H of x is a function of the random variable x. Okay, and the x is a discrete random variable that is defined by sigma of h of x times f of x. That's quite simple, right? So the expected value of the expected value of random variable x is just x sigma of x times f of x, and the expected value of h of x is going to be h of x times f of x. Okay, so here's just example 3.9 Dijkstra channel, but let me skip it. This is really simple. I believe you can understand that example. Okay, and then the other one, expected value sets by linearity. What that means, e of ax plus b, you see that ax plus b, this is kind of linear function, right? That can be expressed as a times u of x plus b. Okay, so completely the what kind of the separated kind of a and b can be out of the e, so a times u of x plus b. This is certain function satisfy this one is called this kind of property is called the that functions as that function satisfy linearity. Okay, and then the variance is a little different. The constant term going to be gone, and then a going to be out of the v, and then take square. It's a square times v of x. So how come? I proved these two in the lecture note. Okay, please look at them. Okay, so please look at them, and then so see. Now the example 3.8 right there, I didn't cover it, but look at this example 3.8. Suppose that the revenue for design B is increased by 10%. Let the random variable U denote the new revenue, 1.1y. Okay, and E of U gonna be E of H of Y, which means that 1.1 times E of Y. Okay, but we already got E of Y in the example 3.8, but I didn't cover it. Please read this one too. Okay, E of Y is a 3.5, so 1.1 times 3.5, 3.85. Okay, and the V of U gonna be 1.1 squared times V of Y, which is 1.1 squared times V of Y is here, 5.25. Okay, so the please review the example what I didn't cover, okay, in your lecture, and then also look at the proof of these two. Okay, it's quite simple. Okay, in my lecture note. Okay, so I covered the 3.2 and 3.3. Okay, so the next time I'll cover the 3.4. So let me stop here.